A geometric series is simply a series where we have what's called a common ratio, or R. And all that means is that we are multiplying by the same number every single time to get the next number. So an example of a geometric series might be something like a sub n is equal to 2 plus 4 plus 8 plus 16, and so on, right? That would be an example of a geometric series where every single time we're multiplying by 2. And if you think back to your pre-calc days when we talked about geometric series, you should remember that there were some geometric series where we could find a sum, and there were some geometric series where there was no finite sum. There was what we called it an infinite geometric series that had an infinite sum, right? And this is one example of that. We see that as we're adding terms, as we continue to add terms, our sum is not going to settle in on any finite value. And if you think back to earlier in our lesson, we actually looked at a geometric series where there was a finite sum. Something like a sub n is equal to 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. So this is also a geometric series, specifically an infinite geometric series, but this geometric series actually does have a finite sum, and that sum is 1 here. It actually does settle in on the value of 1. Well, what's the difference? How come one geometric series had a finite sum and another geometric series didn't? Well, it all boils down to what the R value is, or what your common ratio is for the series. Here we see that our common ratio is equal to 2. Here, in this next series, we saw that our common ratio was equal to 1/2. We're multiplying by 1/2 every single time to get the next term. And what that did was it allowed us to establish that in order for a geometric, an infinite geometric series to have a finite sum, what had to be true is that the absolute value of our common ratio had to be less than 1. The absolute value of our common ratio had to be less than 1. Conversely, when the absolute value of our common ratio was greater than 1, then we had an infinite sum. And we can apply the same concept here when we're discussing the convergence and divergence of a geometric series, because having a finite sum is simply what it means for a series to be convergent, is that it has a finite value for its sum. And that allows us to establish what we call the geometric series test. The geometric series test, or what I'll often say as GST for short. And GST simply says, for an infinite geometric series, if the absolute value of your R is less than 1, then this geometric series converges. And what's nice about the geometric series test is that when it does not pass this test, when the absolute value of R is greater than 1, then we can say that this series diverges. So that's what's nice about the geometric series test. Unlike NTT, or the nth term test, where if it doesn't pass that, it just simply is inconclusive, the geometric series test says, hey, it's either one or the other. As long as your series is a geometric series, if the absolute value of your R is less than 1, then we know that this series is going to have a finite sum, therefore it converges. When the absolute value of your R, or your common ratio, is greater than 1, then this series diverges. So let's look at a couple of examples, and then we'll deal with a couple of other practice problems. So let's look at the first one. First one is written in sigma notation. So let's look at this. Well, here at first glance, you might be tempted to write out all of the terms, but if you think back to your pre-calc days with geometric series, you know that your common ratio is what you are raising to the power of n. So this here is your common ratio. So R is equal to 1/4. And then we can say, well, the absolute value of R is equal to absolute value of 1/4. And what do we know about this? This is less than 1. Because this is less than 1, we know that this series converges. And this is where we're going to start stating the test that proves that this series is going to converge. So we're going to say by GST, this series converges. Now, as a follow-up to this, now that we know this series does converge, it does have a finite sum, let's find that finite sum. And the formula to find the sum of a convergent geometric series is simply your first term, A, over 1 minus R. Okay, so I'll write that here. This is our first term, and it's 1 minus your common ratio. So for this problem here, when n is equal to 0, so let's write a sub 0, when n is equal to 0, let's plug 0 in for n. We have 5 times 1/4 to the 0 power, so that is just going to give us 5. So a sub 0. So I said the first term, but it really just means the first term you're adding, and I should probably specify that. You're adding. So that is the first term that we're adding here in our series. So we say a sub 0 is equal to 5. So our sum is going to be a sub 0, which is 5, over 1 minus our common ratio, which is going to be 1/4. And doing a little simplifying there, 5 divided by 3/4, that's going to give us 20 over 3. And there is our sum. Okay. And let's look at this example, and I'll do this in a different color just so we don't get mixed up. So looking at this, at first glance, we're like, all right, we're given a series. Let's make sure that we know that this is indeed a geometric series and ask yourself, what's my common ratio? What am I multiplying by every single time? And the answer is, well, I'm multiplying by 1/10, right? That's 1 over 10. 0.01 is 1 over 100. My common ratio is 1/10. So we can say the absolute value of R is equal to the absolute value of 1/10. And that is indeed less than 1. So this series also converges by GST. So since we know this series converges by GST, let's find the sum. The sum is going to be the first term that we're adding. In this case, it's 1, the first term that we're adding. 1 minus R, so 1 minus 1/10, and that gives us 10 over 9. So even though we're adding an infinite number of terms, because those terms that we're adding are getting so much smaller as a result of our common ratio, the absolute value of our common ratio being less than 1, we know that even though we're adding an infinite number of terms, the sum of this entire infinite geometric series will be equal to 10 over 9. All right? So I want to do just 2 or 3 more problems with you all, and then give you some time to practice a few of these on your own. All right, so let's look at something like number 5. Let's jump to number 5 because a few of these are going to be easy enough. I think you can try on your own after having watched this video. So looking at this here, can we see what our common ratio is? If you said that the absolute value of our common ratio is 4/3, what we see here, then you would be correct. Now, what do we notice about this? Well, this one, our common ratio here, is greater than 1. Because the absolute value of our common ratio is greater than 1, we can just say right away that this series diverges by the geometric series test. Okay? Now, if you're looking at this carefully, you could also see, excuse me, you could also see that we could have also used the nth term test, and I'll just do that in a different color. Could also use NTT. And what does NTT say? It says, let's look at the limit of our a sub n as n approaches infinity, which is this. There's our a sub n. Well, as n approaches infinity, I don't care about what the limit actually is. All I care about is whether or not it is 0. This is not equal to 0, therefore diverges by NTT. So either one of those tests would have worked for this one. Okay? Let's try another one. Let's go ahead and try something like number 6. And in order for us to determine our common ratio here, we may need to rewrite this a little bit. And at first glance, this might be a little tricky, but if you look at it carefully enough, you can actually use some power properties to rewrite this as the following. We can say that this would be -3 raised to the n minus 1. That hasn't changed. But if I rewrite my denominator as the following, make this 4 times 4 to the power of n minus 1. And just pause and look at that for a second, because we're just using power properties. We're rewriting 4 to the n as 4 times 4 to the power of n minus 1. If we just add up those powers there, we still get 4 to the n. And that's big for us because we notice that I have the same powers here. So this allows me to rewrite all of this as the following. I could say, let's write this as n is equal to 1, infinity. This time, let's write this as 1/4 times -3 over 4 to the n minus 1 power. That's pretty clever. I like that. And just ask yourself then, okay, what is my common ratio? My common ratio is equal to -3/4, but we're looking at the absolute value of this. So the absolute value of this is the absolute value of -3/4, and the absolute value of r here is less than 1. Therefore, we can say that this converges by the geometric series test. Now we're looking to find the sum, and the sum of this series is the first term that we're adding. Well, what is the first term that we're adding here? So maybe I want to just do that in a different color. A sub 0, the first term that we're adding, and when I plug in, oops, it's not a sub 0, excuse me, it's a sub 1, because when we're starting with n is equal to 1, we get 1/4 here. So we're going to write that 1/4, all of this over 1 minus our common ratio, and our common ratio is -3/4. So that would just be 1/4 times 4 over 7, the reciprocal of the denominator, and we get 1/7. Okay? So I encourage you now to try the rest of these problems on your own. Go ahead and check the solutions in Google Classroom, but hopefully you're getting a pretty good sense now of how we can use the geometric series test to determine a geometric series' convergence or divergence, which is really nice about using this test.